Let's learn about resonance. Oops, what's Mr. T got here now? Well, it looks like he's got a device with 3 plastic balls that have different length rods, and they're attached to this very large rod. And then on the other side here, it looks like we've got the same 3 kind of plastic balls, and they too have the same length rods, so they come kind of in matched sets, it looks like here. So let's just see what Mr. T has to do here. Go. Well, what did you see happening? It looked like when he set this one into vibration, this one moved on its own. And when he set this one into vibration, this one moved on its own. And when he set this one into vibration, this one moved on its own. Why do you think that happened? Judging by the look on his face, I think Mr. T has got something else cool to show us. Let's see what it is.
Okay, what we have are 2 identical tuning forks. We have a ping pong ball right here, suspended by string, and the ping pong ball is just resting on the edge of one of the tuning forks.
This was pretty cool. Notice that the 2 tuning forks, one here and one here, are connected to these boxes called resonance boxes, and that the boxes are not connected. So this tuning fork with its resonance box and this tuning fork with its resonance box are separated completely. But when he hit this one, it set this one into vibration, which made the ping pong ball move. Pretty cool. But again, we have to ask, why did this happen? And why is it that these 2 tuning forks had to be exactly identical? If the tuning forks were different, this would not have worked. Let's apply what we've seen to waves on a string. So in this simulation, here's the string, which is fixed at this end, and at the other end is an automated device which will regularly send waves down this string. And this device I can set the frequency of. So I can set how far, at what rate this moves up and down, making waves. So let's first of all just watch and see what happens here as we use this particular frequency. And I can see that the waves just kind of jumble around, nothing too organized. Now what's going to happen is we're going to set the frequency from 31 to 50 and see what difference that might make. Now if you notice, over here it's going to seem like we're shaking it at just the right time. And as a result, the waves are getting bigger and bigger and bigger and bigger. So we get 2 very different behaviors of the waves on the string depending on the frequency of this device. So notice that there are 2 things here with frequencies. One was the wave, which the waves are now so big that we can't even see them on the screen, and the other is the frequency of the thing making the waves. Now in this device, I have 5 masses, 1, 2, 3, 4, 5, all connected by springs to this platform. Now the platform is connected to this driver. So this driver is able to make the platform move up and down at whatever frequency I set this to. Now the masses are connected by different springs, and as you're going to see in a moment, these springs vibrate at different rates. So you can see that by the time we get to 4 and 5, clearly 4 and 5 vibrate at a higher frequency than 1 or 2. So what we would say, terminology that we would use, is we would say that each of these guys has a different resonant frequency, which is the frequency that the device wants to vibrate at. And there's only one frequency that each of these guys wants to vibrate at. And now what we're going to do is we're going to see what happens as we start to set the driver at different frequencies. We're going to watch what happens to them. So we first start out at a very low frequency. And you can see this guy is moving very, very slowly. But it's starting to pick up in frequency. And now it's very close to the resonant frequency of number 1. But then as the frequency down here begins to increase even more, now we get close to the resonant frequency of number 2. And then number 3. So as we steadily increase the frequency down here, now we're matching number 4's resonant frequency. And then finally we match 5's resonant frequency. Notice when we're matching one object's resonant frequency, the other ones do not vibrate. Now if we think about energy, what's happening is the driver platform is able to provide energy for each of the 4 masses. 5 masses. And what happens is it's only able to put energy into the mass and spring if it's at the resonant frequency. If it's not at the resonant frequency, energy is not transferred into it. So resonance is a situation where one device vibrating at a certain frequency transfers energy to a second device, but only at its resonant frequency. So resonance is a phenomenon where one vibrating object causes another object to vibrate at its natural or resonant frequency. And when this occurs, energy is transferred into the object. So now we can see how these demonstrations that we viewed at the very beginning work. First of all, in this apparatus right here, we saw that when these 3 balls were set into vibration, they caused the corresponding same length ball on this side to vibrate. And the reason for that is when, let's say, this one was set into vibration, it produced a particular frequency of energy that was passed through this bar over to these 3 guys. And all 3 of them were presented with energy of that frequency. However, only this one had the same resonant frequency as the energy that was coming through the bar, so only this one was set into vibration. Likewise, when this one was set into vibration, it caused a certain frequency to pass through the bar, which only this one would be set into vibration by, because only this one's resonant frequency matched that one. Likewise, in this setup here, you hit this tuning fork, which causes this tuning fork, which is not connected, to vibrate. Since these two tuning forks are identical, making this one vibrate produces sound waves of exactly the frequency that matches the resonant frequency of that tuning fork. So hitting that tuning fork caused this one to vibrate. So this is an example of resonance, where one object vibrating causes a second one to vibrate at its resonant frequency. If the tuning forks were not matched, then this would have produced a frequency, but this resonant frequency would have been different, and therefore it would not have worked.